Good afternoon, everyone. Thank you very much for inviting me today. So this is my first time visit supercomputing or HPC conference. And my name is again Yoshitaka Ushiku. And today I would like to talk about embodied AI for science. This is a story about how AI goes beyond the screen and starts working together with us in the real world, this physical world. Okay, before diving into the technical part, let me first introduce a broader initiative called AI Robot-Driven Science, or AIRS in short. So AIRS has three pillars. First, people. Yeah, of course, we are building a community platform to connect researchers and developers across disciplines. And second is knowledge. We aim to systematize and standardize research infrastructure for AI-driven science. And third, outside. So we would like to have the international collaboration and partnerships with industry and academics. So this talk is also a part of this effort. And unfortunately, we have our next meeting tomorrow in Tokyo. So sorry for overlapped schedule. But if you are interested in such kind of initiative, please don't hesitate to visit our website. And there are a few words about myself from my side. So I started my career working with research topic, a kind of vision language, which is an intersection area between computer vision and natural languages processing. So, such as image captioning and cross-media retrieval. Over time, I became interested in a question. So what happens when language meets the physical world through the robot or some very wise agents in the world? So that question gradually led me from pure computer vision or pure natural language processing research team to AI for science topics. And finally, to the introduction of robotics. So at OMRON SINIC, by the way, do you know OMRON Corporation? Maybe Japanese a little bit familiar with that corporation. So which is a corporation for factory automation and partially healthcare services. So this company has several research topics about AI or robotics for factory automation originally. So this OMRON SINIC is a research institute having three groups. One is for smart operation using robotics, and the other is a smart learning using cutting-edge AI technologies, and the other is HCI part. So interaction between humans and robots or humans and AIs. So I worked in an open innovation research institute here. There I learned an important lesson. So real-world impact requires real-world experiments. So this is why my current research direction becomes a kind of AI for science. So let me share a long-term vision. So this is a short description, short introduction of Moonshot program. This program is a national research program, originally designed by Dr. Kitano, who is a keynote speaker this morning. And in this program, our project has a final goal. By the end of 2050, we aim to create AI robots that can produce Nobel Prize-winning research together with humans. So not replacing scientists in the world, but collaborating with them. And this may sound ambitious, but as I will show today, this foundation already exists. So to accelerate this vision, we founded a startup called NexaScience in October 2024. It is a spin-off from a Moonshot project, and our goal is very simple. So turning cutting-edge AI for science research into real-world systems and services. Research alone is not enough, but we need implementation in the world as a service to accelerate such kind of AI for science. But AI for science is not new topic. In the 20th century, originally systems like Dendro and Prospector already aimed to support scientific discovery using the second AI generation technologies. So they were very impressive, but they shared a common limitation. So they could reason, they could come up with some hypothesis, but they could not experiment. So could not conduct their hypothesis in the world. So in the 2000s, a key idea emerged, embodiment. Ross King's robot scientist Adam, shown in the left, could generate hypotheses, design experiments, and physically execute them. And this closed loop between thinking and doing. So the other example is shown in the right side, kind of chaotic system to rediscover physical laws. And then in the 2010s, then came the deep learning revolution. So with models like AlphaFold, AI demonstrated extraordinary predictive power, but prediction alone is not science again. So science requires interaction with the physical world using the robots like this. So recently, AI and robots have begun to merge again. And the robots now automatically optimize catalysts, as shown in the left side. For example, mobile robotic chemist from the University of Liverpool. And another example is Labordroid Mahoro in Japan. Also improves the cell culture recipes without human intervention. And this is no longer future talk, it is happening today. Okay, then let me talk about the brief highlight of some our research topic. First is IRIS, shown here. So this is a kind of open source software to automatically conduct AI research. So our goal is full automation, from paper search to hypothesis generation to experiments analysis and even paper writing. Okay, let me share an example of the generated paper using IR system. There is no time to take explain in detail, but the generated paper is for AI topic basically, and of course it includes abstract part, introduction, related work here, and backgrounds using some method and experimental setups, and of course the results using some plots. Discussion about them is somewhat short, but they are also conclusion part and references. So nowadays we can generate a kind of workshop level of AI papers fully automatically. And however, to automate such kind of research, we must teach knowledge to foundation models first. So next part is this topic. So this turns out to be surprisingly difficult to teach some outside knowledge to existing large language models. So suppose that you have new domain data here, and that you want to utilize during research via chat large language model. So a popular solution is retrieval augmented generation, or RAG in short. But it works well until documents become long. So retrieve document length is very important. There is a known phenomenon called lost in the middle. So when the input context is too long, extracting information from the middle becomes difficult. So this is an example of the retrieved context using for new domain knowledge. This is a little bit long, and the information required to answer the question is placed in the middle. Then the accuracy to extract the information from the context and answer the question correctly becomes low in comparison to the other places. So another approach is supervised fine-tuning, of course. So you have the pre-trained LLM, you can teach the new domain knowledge using the fine-tuning technology, and then chat large language module can directly utilize the knowledge. But we discovered a new kind of position bias problem here too. So if the answer appears late in the training documents, accuracy drops again. So here is a documented example to teach something to the large language models. But the information is, if the information is described in the latter part, the accuracy to answer the question would be dropped. So to address this problem, we propose using a denoising variant of autoregressive supervised fine-tuning. So the key message, the very important message here is very simple. How we teach knowledge matters as much as the model itself. So the left side shows that the simple idea enlarging the model itself is not so effective. There are also the problem of the positional bias. But if you adopt the denoising autoregressive SFT, the problem is very reduced. Okay, then let's move on to the third research, material property prediction from crystal structure. Crystal structure are periodic and effectively infinite. So standard transformer networks struggle with them. So by respecting physical structure and of course AI design, we can design better transformer architecture model for such kind of material for science. So such research requires understanding both AI and chemistry, of course. And Dr. Taniai at OMRON SINIC X is an expert of this domain. So let me introduce him and his research by showing his short introduction video.
We introduced our paper titled Crystal Former Infinitely Connected Attention for Periodic Structure Encoding. Our work is an interdisciplinary study in machine learning and materials science, which is a field to explore new useful materials such as superconductors and battery materials. Materials are represented by crystal structures. They are infinitely repeating periodic arrangements of atoms in 3D space, described by a minimum repeatable pattern called a unit cell. We here focus on the problem of predicting material properties such as formation energy and band gap from a unit cell of a crystal structure via neural networks. Machine learning-based prediction is much faster than DFT calculations and is useful for accelerating material discovery and development processes. Property prediction is usually performed by neural networks that hold state features for the atoms in the unit cell and update them via interatomic message passing layers. For property prediction, it is important that these networks are invariant to input data transformations such as rotation, translation, and periodic boundary shift. Material representation learning has evolved along with advances in machine learning and molecular representation learning. Particularly, graph neural networks, which have increased their popularity since 2015, are now main approaches in molecular and crystal representation learning. Against these mainstreams, a transformer-based, fully connected self-attention network called Graphomer showed its effectiveness for molecules. But whether such dense attention is applicable to crystal structure is still an open question, which we tackle in this study. Okay, let's start with the simple transformer for molecules.
But let me summarize the technical details. So in short, we redesign the attention mechanism to reduce the number of the tokens we must handle to predict the property of the crystal structure, which is infinitely repeated. So by redesigning the attention mechanism, we can successfully reduce the number of tokens which should be inputted into the transformer architecture from infinite number of atoms to tens or even a lower number of atoms in a unit cell, in a single unit cell. So our experimental results show that both efficacy about the computation and the accuracy to predict such material property. Okay, then next part is our research highlights in robotics. So one shown in the top right here will be explained later. So let me explain about this one. Science is full of hard physical tasks such as powder manipulation. So powders are difficult to see, of course, difficult to handle, and difficult to measure. So by combining vision, sound, vibration, and symbolic planning technique in the robotics field, robots can finally deal with powders. So this is where embodiment truly matters. Let me introduce this research robot example that automatically weighs powder. So in many chemistry of materials science, weighing milligram levels of powder is a daily operation. It's a bottleneck for automation. So the challenge here is that the powders behave differently. So some flow smoothly, others cramp, and small mistakes cause scattering and messy cleanup. So collecting such data in real world is impractical. So the solution here is the use of simulation. And then, yes, so we use domain randomization technique and finally successfully powder weigh through the robot. So the takeaway message here is, if we want robots in real labs, we must design learning setups that minimize risky real-world trial and error. So simulation is not just cheaper, but it's sometimes the only realistic solution to come up with such kind of automation. So now a closely related task, powder grinding, is the third example. So like using a motor and pestle, but not by hand, but by robot. So such kind of grinding matters because particle size of powders affects downstream experiments, but it's hard to observe during the process, of course. So their previous system used only vision, which is good for seeing, but not for estimating how fine the particles are. So this paper's key idea is very intuitive: add audio information. Because the sound during grinding carries information about correct and contact state and the material status. So the robot uses audio-visual feedback, not only seeing but also listening, to choose better action in the loop. For non-robotics researchers, the big message here is, in the real laboratories, one sensor is rarely enough. So multimodal signals such as vision and audio are often the difference between demo and deployment. Finally, let me connect these robots to a bigger trend, foundation models for robots. So this leads us to a broader concept, physical intelligence. So this is a demonstration video of the physical intelligence in the United States. So such intelligence does not live only in neural networks. It emerges from interaction with the physical world. So this figure summarizes a model called Pi0, a vision language action model by physical intelligence. So the idea is starting from the pre-trained vision language model here, which already has internet scale semantic knowledge. Then attach an action expert, shown here, to produce robot actions. So in Pi0, the action part is trained with a flow-based or flow-matching style architecture, which is different from standard autoregressive token prediction in large language models. And crucially, the model runs from large, diverse robot datasets, like OpenX embodiment datasets I explained later, so that it can generate across tasks and platforms. For the audience, I want you to remember one simple point. So we are moving from models that talk to models can do. So once we can connect large language model to action reliably, lab automation becomes a software problem and a data problem, not just a hardware problem. So from vision and language navigation, originally started from 2017 to embodied question answering to RIKEN. Foundation models are becoming the interface between language and action. So let me play this video again from the start. Here, yeah, this is a very famous research, so many of you may know. The user input shown here, I spilled my Coke on the table, and would you throw it away and bring me something to help clean? It's the input. And the other input is sensor information from the camera of the robot. Then the robot starts thinking, and the log of the thought by the robot is shown in the bottom. So the robot first find a Coke can and pick up the Coke can and go to the trash. And then it starts to find something to help cleaning. And finally it finds a sponge for cleanup and pick up it and bring it to the table here. But note that this video is highly speeded up, as shown here. So it's 10 times faster in the real world, which is very different from the demonstration by the physical intelligence in 2024, because this demonstration is almost in real time. So this is why this demonstration is very impressive and surprising to the world. And as I said, commoditization of the dataset for such kind of vision language action model is also very important. So this OpenX embodiment collaboration is a collaboration among a large number of academic laboratories and research institutions to collect such kind of 1 million episodes to train such kind of the model. So finally, let me introduce our work for such kind of the embodied AI. So we use large multimodal models to generate symbolic plans. We use LLMs, not only for controllers, but also for planners. I mean plan to generate some problem descriptions, which is a kind of JSONs-like size format to describe the planning of the robot itself. So the part to generate such kind of plan, we utilize a large language model and a large vision model, language and vision model. So there are two streams to come up with such kind of robot planning. One is current ones by using large language model to design such kind of robot planning. But also there are very traditional approach which we use symbolic planner, which is a kind of compiler to automatically convert from the problem description to actual plan for robots. So by integrating these ideas, we can both produce some planning and automatically correct it if there are some logical error in the problem description. So there are three parts: object estimator to estimate existing objects there, and the initial state estimator, and the goal estimator to estimate what is the task described here. Then some errors in the problem description can be corrected automatically and then conducted by the robots. Okay. So to conclude, embodied AI for science is not a distant dream. So it is already happening. But no one can build such kind of AI robot system for such kind of realistic research alone. So if you are interested in AI, robotics, or science, I would like to invite you to join AIRS again. So let's build the future of science together. Thank you for listening.